sir. Now let me move on to my presentation. My name is Joshua Partheepan. I am an assistant associate professor at West Texas A&M University, and my project is on hydrogen gas turbines or oxy-hydrogen combustion and gas turbines. So just an overview, just 101 energy. Uh, we are kind of in the 21st century. The ability for us to move away from carbon and the public perception, energy security, all fuels in for the renewable energy growth in the sector for about 7% in 2020. And it has been consistent for the last 4 or 5 years, which is great because if that trend continues, then you will see extended amount of renewable energy by 2050. Consumption of all forms of energy increased in the United States between 0 to 15% from 2022 to 2050, which is great because even though it's about 30-year time period, we are not necessarily increasing our energy consumption, thankfully because of all the conservative measures that we are going to implement in the future, which help us to reduce our energy usage even in the future. But that's not necessarily the trend around the world. So you will see a significant amount of energy increased, almost about 50% in the next 30 years, especially from the developing countries. And also, there will be a shift in energy usage from other sectors, like if you're using gasoline, if you're using natural gas, you might see all those energy uses being converted to electricity usage in the future. One of the major problems in 2050 is how do we feed 9 billion people and how do we tackle the water usage for those 9 billion people, especially the freshwater usage. And another big challenge along with those lines would be is how do we power all our needs in 2050 with possibly green power or carbon neutral power. So this is at present in US, we are about 21% renewable, nuclear about 18.2, coal 19.5, and our major share, roughly about 40% from natural gas. If you see the world trend, just the coal and natural gas is a little bit reversed. So you will see a lot of coal power plants in and around the world, and then you'll see about 20% to 25% natural gas, and then about 10 to 15% nuclear. Interesting enough, you will have a little bit of higher renewables in and around the world, thankfully because of the hydropower, especially in Europe and all China and some of the other countries which has more power. That trend is going to pretty much stay almost the same, which is surprising in 2050. So if you see the energy trend going from 2020 to 2050, you can clearly say that developed countries, US, Canada, Mexico, Australia, most of the Europe, their energy usage is not going to change much. But the energy usage in all the developing countries are going to change significantly higher. And that's the trend that you would see in there, which correlates with the world population increase and the GDP increase in those developing countries. And this would be what the energy mix is. What I might say is look into the reference. So we will still have coal power plants in 2050. It might be decarbonized, I would assume, but we are going to see a significant share of coal, nuclear, and natural gas power plants in 2050. But there will be a significant increase in solar generation and some increase in wind power, which I believe the next graph is going to give you a rough reference. So if I've collectively summarized this, about 1/4 of the energy is going to come from coal, another 1/4 from natural gas, 1/4 from solar, and collectively wind and nuclear will contribute the remaining 25%, which is kind of interesting because it kind of, all the previous 4 slides tells you a picture that power plants are not necessarily going to go away anytime soon in the next 30 years or so. You're going to see natural gas and coal power plant almost contributing 40 to 50% of electricity in 2050 around the globe. And I can kind of sense why we need power plant, maybe referring back to this graph. So that's the California duck curve. And one of the problems is basically if you start installing a lot of solar, then the conventional power plant needs to reduce their energy usage significantly, which creates a lot of unintended consequence in the power system. To the extent that because the solar production is so high, they almost gone negative in 2023, meaning they over-generated in that scenario. And another problem is, so let's say the solar is peaking in the middle of the day, so more of my solar is coming in here. But as it gets to the evening period, my conventional power plant needs to start ramping up right from there to right up there. That's a big swing for conventional power plants to ramp up that quickly, which brings in another problem with frequency control because that is solar, which means it's inverter driven. So there is no dynamic spinning reserve or there is no moment of inertia in the system. So if there is a voltage drop and if it's big enough, then it would pretty much take the entire grid out. So the three main problems: short, steep ramps of power generation, overgeneration risk, decreased frequency response. And I think that's the contributing factor for power plant to exist even in 2050. So this is the scenario for Texas. So that's a 2021 energy load for Texas. We have our peak loads during summer, and one exception is the 2021 storm, winter storm. So we used quite a bit of energy during that particular time. So if I overlay that with wind, because wind is more predominant here, then that is what it's going to look like. If I go for 70% wind, then that's what it's going to look like. And that's a problem as well, because it will have its own curve in terms of those short, steep ramps and frequency response problems, kind of from state to state. So it's not only limited to solar. That problem will exist in the wind market as well, or a collective hybrid of wind and solar. So everyone knows storage would be a solution for it, but how effective is it going to be in terms of meeting those loads, and what kind of storage are we talking about? So there, because we are referring a lot to power plants, our objective or my research objective is how can I take the power plant like concept and try to make it more greener in nature, try to be more dynamic, more resilient, more lifespan cycle, but still have a significant advantage over other storage systems. So one of the technologies that I really like is looking into rocket engines. So that is a J2 engine test that has been conducted in 1966. And all the white thing that you see is basically steam. So because the engine uses hydrogen and oxygen, when you combust it, the only thing that you're going to get out of it is steam. So to put it in a perspective, if I take that engine and if I'm using all that steam in a conventional power plant at 33% efficiency, I can meet Texas peak power by 10%, or the collective peak power of US by about 1%, just one engine. And that's because of the capacity of oxyhydrogen combustion. So then I thought, is there any technology that is in existence that can capture that steam? Because that's an open combustion, so it's easy. But is there a closed combustion system in existence? Yes. Germans did a research in 1980s era. They were trying to use that for power plants, conventional power plants. So was Russians. Russians are currently investigating how they can use oxyhydrogen combustion for generating steam, which can be used in conventional power plants. So then we thought we should also invest into it. We should also start researching into these kind of technologies because they're all very close patented technologies. So if we are going in that route, why not we figure out our own technology as well? So we have 4 patents, 2 in the nozzle system itself, thanks to 3D printing that made it way easier for us to prototype it, test it, and then we also moved on from the testing phase of the nozzle to the combustion chamber itself. And we were able to successfully design, develop, and test a combustion chamber which is able to generate steam at whatever pressure you want and whatever temperature you want. So the concept is basically you take hydrogen oxygen, you burn it, it's going to burn at 3600 degrees and it's going to generate steam. The challenge is anything at that temperature is going to melt, any metal that you put in. But because it's steam, it doesn't really radiate energy. So as long as I build an envelope around the flame, and if it doesn't touch the flame, I'm fine with it. So now I'm using water to cool the envelope, and that water becomes steam, which I'm carefully introducing back into the chamber to regulate what temperature I want the steam at. So by controlling the amount of water that I have and the pressure of hydrogen and oxygen entering the chamber, I will be able to control what my exit temperature of steam and what my exit pressure of steam that I want it as. So now it has opened up multiple applications for me because I don't necessarily have to take this and put it in a steam turbine power plant. I can also use it in conjunction with the gas turbine power plant because there is a concept called steam injected gas turbine where I can take the steam and replace the exhaust flow gases with steam in a gas turbine, which would almost give a better efficiency when compared to an exhaust gas flow. So this is the characteristic of a hydrogen oxygen steam generator. So you're looking at a temperature range anywhere from 500 to 1800 Kelvin, whereas in a conventional boiler, you're looking at 500 to 900. This is a direct mixing process rather than an indirect radiation, convection, and conduction process. So the efficiency is really high because of direct mixing. So you're looking at 98 to 99.5 efficiency, irrespective of what your cycling is. So even if you're cycling at rapid rates, that efficiency pretty much stays the same. Scale of unit, you're looking at 10 to the power of -3 meter cube per megawatt. So it's relatively really small for a megawatt system. So if you're talking about a 10 megawatt system, you're collectively looking at the size of this table. Not necessarily because of the technology, but because of the capabilities of oxygen and hydrogen combustion. And then starting time, less than a minute. Of course, it's a rocket engine, just repacked in a different version. And then load swing, 50% load swing, less than a second. Again, because it's a rocket engine. Well, the combustion chamber can handle that. Not necessarily the turbine or any of the downstream equipments can handle it. It just tells you what the capability of the system, not necessarily the plant itself overall. Pollution, there is no pollution because you have taken hydrogen, oxygen, you have combusted it, generated steam, and you're running it in a closed system. So there is no pollution of whatsoever in this system. So then if I take that system, what are those applications? I can come up with different applications. One of the instant applications that we can think of is because it produces steam, now can I use it in a coal power plant? Yes, you can. You simply eliminate the boilers and you eliminate all the downstream equipments after condenser. So you don't worry about any of your dust collectors, ash collectors, selective catalytic reduction, ESP units, any of those. You can forget all those units. And you can also forget about the ID fans, FD fans, and all those things because everything is handled by the combustion chamber. So all you need is hydrogen source, oxygen source, and then the combustion chamber. Then you're basically taking the steam at whatever temperature you want the turbines to operate, inject it directly, and run the power plant. Right? Will you gain any efficiency because of this? Yes, you will, but it would be minuscule. It's not a lot of efficiency gain. So you're still operating your power plant roughly about 33% efficiency, but it's very much possible. Can you implement it as a pilot scale in a power plant? Yes. If you want your power plant to have a bigger load swing, your boiler may not be able to handle the steam delivery. So what you do is you put this system alongside with your boiler so it produces auxiliary steam which can quickly ramp up or down your conventional coal power plant. Can I use it in a combined cycle plant? Yes. And this is where it gets exciting because now I can take a conventional power plant and what I can do in this sense is I can remove the compressor out of my gas turbine. And why? Because in a conventional gas turbine, I'm sucking the air, compressing it, running it through the combustion chamber, and then into the turbine. In here, because there is no air involved in it, I don't have to compress anything. And usually, hydrogen and oxygen are stored in a compressed format, minimum of about 300 bars. So my gas turbine operates roughly at 30 to 90 bars, so I don't have to worrying about compressing my hydrogen and oxygen. So in that case, when my pressurized hydrogen and oxygen is supplied to me, all I have to do is figure out from the burner section. So I don't need compressor. So I burn my gases and then I produce steam which is equivalent to what my hot gases that I would get out of combustion chamber and run it through my gas turbine. Gas turbines will handle steam just fine because most of the high performance jet engines during 1980 era actually used to have or inject water into the gas turbine to gain performance at higher altitudes. So it was a very established system, not necessarily in use in a conventional power plant setup, but it can be used. So conventional gas turbines can be converted to steam injected gas turbines, which gives you the same efficiency. So now downstream of the gas turbine, you still have hot steam coming out of that. So you run it through the heat exchanger, which is your HRSG. The only difference is you're extracting heat from steam, which is used to convert water to steam in the steam turbine cycle. So you're not really touching the steam turbine cycle, you're just running it like a traditional gas turbine cycle, still extracting the heat and running the steam turbine cycle. And of course, there won't be any downstream equipments after the HRSG in terms of any pollution control, because you don't have pollution control there as well. The one thing that you might have to add is you might also have to add a condenser to cool down the low pressure, low temperature steam, which can be recirculated again in the system. Not necessarily there, but you might have to use it for your hydrogen oxygen generation. So the water, whatever water you get in, you feed it into your electrolyzer, which brings it back into the system. Now, what would be the efficiency like? So again, the system that we are proposing, it's not necessarily new. There are several patents that are in existence back from 1990. But one of the things that we did is we studied all those patents, and one of the problems with those patents is they have either so high thermal specific load in the turbine component or in the heat exchanger component or in different parts of the system, which we try to avoid by minimizing or playing with the numbers and trying to reduce it so that a current turbine will be able to handle the load when you switch it from a natural gas fired unit to a hydrogen oxygen combustion fired unit. And what is the theoretical efficiency that you're looking at? Roughly about 70%, right there, 70 to 60% LHP or a HHP. So is it pretty practical to get those efficiency? Yes, it would be practical. Again, because of no pollutants in the system, no other auxiliary units that are going to be present in the system. So then, can we push it even further to a futuristic system which can handle those loads? Yes. So in here, this is basically a modified system, modified gas turbine system, which does not necessarily have the steam turbine component to it. So what you're doing in here is you are taking your hydrogen source and you're taking your oxygen source. Both are compressed in nature, firing it in the combustion chamber, and then converting it into steam, running it through your turbine, which powers the generator. Then the hot exhaust gas that is coming out of the turbine, roughly about 600 degrees, 1.5 bars, you run it through your condensing HRSG, which helps to extract all the heat in another water stream. This water stream is basically going to pick up the heat almost in a subphase, which is basically like superheated water that can be injected into the combustion chamber for cooling purposes. So that way, rather than having a separate system that runs the steam turbine, you're basically extracting the heat to run your gas turbine system, thereby increasing the flow of steam that runs through this system, thereby increasing the efficiency. Not by much, maybe by 1 or 2%, but the biggest thing is reduction in components in the system. So rather than having two separate cycles, two separate turbines, you're boiling it down to one bigger gas turbine, which is much more resilient in nature. So what would be the efficiency, operating efficiency? Roughly about 58 to 60% in efficiency, but with much more reduced components in place. So then we thought about where would this system fit in terms of pricing? Is it going to be very expensive compared to any of the systems in the market? Not necessarily, because the combustion chamber and compressor system is out, which means you are reducing the gas turbine by 50%, which is what the cost that I would assume to build a combustion chamber for the hydrogen oxygen system. So again, there is no special components or anything in there, just normal design, engineering design that our graduate students were able to put together and build it. So it's not necessarily any complex design, it's just 3D printed rocket engine in a miniature form for power generation applications. So I would assume in a combined cycle system, the pricing would be very similar to what a conventional combined cycle system is. So then, if I start talking about economics of hydrogen oxygen, what are all the different factors that involves that determines what my price of electricity is going to be? One would be the capital cost of the power plant, which I said it would be pretty similar to what a combined cycle conventional power plant is. Then the second would be operating cost of the power plant, which depends predominantly on the hydrogen, not necessarily on the maintenance of the power plant. And then capacity factor, that plays a major role. Am I turning on my power plant only 10% of the time, or am I going to run the power plant in a consistent manner? And then my hydrogen source and my hydrogen storage comes into play as well. Hydrogen storage is an interesting thing, because if I'm trying to run my power plant at a 50% capacity factor, then I can use salt caverns or any underground storage that are in existence for natural gas. So that's interesting, because natural gas on a large scale can be stored underground in the underground caverns, which can be used without much modification for hydrogen storage as well. So that would be one of the biggest benefits, and it can hold hydrogen gas for up to 6 or 7 months, which is what a typical gas natural gas system would use as well. But hydrogen source kind of plays into existence, because are we talking about green hydrogen or are we talking about brown hydrogen, drastically affects the price of hydrogen, which also drastically affects the price of electricity that comes out of the power plant that we're talking about. So some estimations that I was able to put together, today's hydrogen cost from electrolysis, very optimistic number, is about $6 per kilogram. By 2030, hydrogen generation from low-cost renewables at roughly 2.5 cents per kilowatt hour or $25 per megawatt hour, with a capacity factor of 50%, yields a cost of hydrogen at $1.7 per kilogram. Now, if I factor in that I'm storing the hydrogen at underground storage for a long period of time, that would add another 30 cents to the kilogram of hydrogen, making it $2 per kilogram. If it's $2, and if I'm using it in a combined cycle power plant with 60% utilization factor, then I can deliver power anywhere from $100 to $180 per megawatt hour. In other words, from 10 cents to 18 cents per kilowatt hour. If I'm using it in a normal simple cycle turbine at 25% utilization factor, which is predominantly going to be a retrofit, then I can deliver it at 20 cents per kilowatt hour. If I'm retrofitting a coal power plant at 50% utilization factor and about 33% efficiency, then I can deliver at 30 cents per kilowatt hour. So these are really optimistic numbers. But if you want a realistic number, I would say in a combined cycle newly built power plant, we might be able to deliver it anywhere from 18 cents per kilowatt hour to roughly about 30 cents per kilowatt hour, depending on where the hydrogen is coming from. Now, thankfully, I'm supposed to present first, but I let him present first. So if he can deliver hydrogen at under $1, then we are talking a different story in the economics there. Because that might make my life so much easier because hydrogen technology is there, the utilization factor for using it in an existing power plant framework is there. It's just the cost would be the most prohibiting factor in the scenario for a mass transition. If the cost of hydrogen from different sources is reduced significantly, then we'll be seeing large scale power plants using oxy-hydrogen combustion system in their systems. And these are my references. Fine print, yes. Thank you. Any questions?
Can you go back to the slide where you had the peak load and throughout the day? Because I think people don't necessarily understand that chart a lot because I see what you mean, but so like if you were to picture nuclear, like you can keep nuclear at a steady rate, and then on those off-peak hours, you can produce the hydrogen and get it ready for the peak hours later. So you can create
This might be a better.
That's a really good chart, but a lot of people don't realize how delicate the grid is when it comes to integrating solar in it, because a lot of times solar can actually increase your carbon footprint, because then you've got to turn on your gas plant that much higher, scaled up in the night, and you're eliminating other sources of power during the day.
Does that apply to new models of integrated solar, so that when you're looking at an integrated with microgrids, with storage, are the economics?
The storage, I mean, that's what it's.
No, storage like lithium ion or zinc ion or.
That was my question, is how does the storage come into play when it?
No, my question, I'm sorry, when you're talking about solar, your assumption is what we're doing right now, but there are new models that are coming out that are integrating solar generation with bundled with storage, with long-term storage, with microgrid technology, so that you have intelligent efficiency with the energy we're using, but an integrated solution. And so the assumptions you're making about solar now, I understand, but these new models that are coming into play, are you familiar with them? And if so, how do the economics work with that?
I'll get into some of that in mine, actually. I write them down, so whenever I'm about that.
Great, thank you.
I would just say that if you have to store it, you're going to lose a lot of energy, because you have to put it into a battery and then take it back out. So I guess that was my question, is how hydrogen, because if you've got hydrogen left over and you're keeping it here, you're not losing any energy burning hydrogen later as opposed to right now. But for the solar, and especially if you want your uptime, as they say, you've got to build. So if you want 1 megawatt worth of generating capacity, you're only going to get about 1/3 of that out of there. So you have to build 3 times for that to get your base load. And then if you store it, you have to do 3 times that again, right? So you have to do. So if you want 1 megawatt of current steady power, you have to build 9 megawatts or something like that worth of power.
Yeah, it's anywhere from 6 to 8.
Yeah.
Speaking, at least current models are that way, from a storage perspective. The challenge with hydrogen, one, if you can store it efficiently, store it reliably,
Like leaks.
then, well, yeah, it's pretty small molecule, right? You gain a huge step ahead with regards to the economics of it. So there's the storage component of hydrogen specifically that's just generally not scaled at this point. And then I think he hit on it a few times that the cost to produce the hydrogen, wherever you're getting it, right? If it's a byproduct of something else where you're using an electrolyzer specific to generate it, there's a significant efficiency loss in the generation of the hydrogen if you're intending on using it as a fuel. So again, if you can pair it with something where your generation cost of the hydrogen is relatively cheap, and then you can store it relatively efficiently or cheap, then yeah, it's a huge alternative. And now we're getting into energy storage rather than physical application of burning the hydrogen as fuel. So it gets into the storage economics But like, again, from a cost economics perspective, lithium ion for this application is significantly cheaper by today's technology. Eventually we can get there through the whole decarbonization effort, but,
You mean solar is cheaper to store than hydrogen, is what you're saying?
well, significantly.
Yeah.
But
That's free, right?
but then the system is so hydrogen storage on large scale, not in existence for power plants, right? But it's very much in existence for oil and gas industry. You drive down to Houston, you're talking about 100 tons of hydrogen stored on a daily basis and shipped around, no problem. So it's just a different industry that we have to learn from. So handling hydrogen on a large scale, storing it on a large scale underground was a proven technology for oil and gas industry, where they use hydrogen in refineries. So am I getting my hydrogen from natural gas um, conversion process? Then it's very cheap and easy to handle and easy to transport around as well. Now, the question though is, at what scale am I going to use my power plant, right? So if I have a complete PV system, then that PV system on a net to net scale for my load will only supply about 1/3 of my energy, right? So the remaining scale, so this is where my PV is going to come in. So the remaining sections, which is about 60% of the power, needs to come from some power source. Yes, batteries can contribute to it a lot, but then you also have to have a rotating mass in the grid. So when you're in a microgrid environment, batteries work excellent because you're talking about not transferring the power over long distance. But if you're transferring power from here to a longer distance, you need to have a rotating power plant in the system to provide the dynamic reactive power. So that's where these kind of power plants come in key. And then the second thing is, if I capture the hydrogen, this would be more apparent in the next one, because in Texas, my winter load is nothing. It's roughly about 40 gigawatts. But my summer load is roughly about 80 gigawatts, almost the double. So here in West Texas, the wind is very prominent right in the winter months, but not so much in the summer months. So now I have an excellent opportunity to capture all these excess power in this region and in here, and I can put it in the salt caverns, which is also very prominent in West Texas, and store it for up to 6 months and then deliver it during my summer peak times. So that is possible because of hydrogen. So those are the scenarios that you'll be looking at where hydrogen might make much more sense over a large amount of power stored over a long period of times, where it make much more economic sense.
And your method of creating hydrogen varies dramatically from, like, if you use electrolysis and you just from pure water, or if you take it from methane or hydrocarbon or something, it's a lot easier to break up apart.
What are the costs for ground
It-
hydrogen? Hydrogen's not my specialty.
It's about $1. But if you're talking about electrolysis, it used to be $10. Now it has came significantly down, so it's about $6. If nuclear, there's also other technologies that are in the market, which are concepts. So they say they can deliver hydrogen at 40 cents per kilogram, which is possible. We just need to get there, and that would be the thing that plays very much into the hydrogen economy.
Would they be using the nuclear electricity to run electrolysis to do that, or is the hydrogen actually being produced within the reactor? Is that what you're saying?
So if I'm using the nuclear, I would pretty much take natural gas and use the heat to split natural gas to hydrogen.
Okay, so SMR.
Yes.
Right.
Yes.
Yeah. Yeah, that's a problem with, you mentioned natural gas, and you can make hydrogen easy from natural gas that's been around for 100 years. But the problem with it is the carbon dioxide emissions from it.
If
So
you
yeah,
do,
but
if
carbon
you
capture-
do steam reforming
Right,
instead of just pyrolysis.
but
So
you
there's pyrolysis, there's
Right.
steam reforming, and then electrolysis.
Right, yes, yes.
Is the three main methods.
But the carbon capture would then add to the cost, but it's interesting because if you use the nuclear part of it, you
Yes, yes. So there is like multiple systems. That's why I don't really touch the hydrogen price because there is a lot of factors involved in it of how you control the pricing. But let's just say you get hydrogen at $2, then I can make this plant work. That's how I kind of simplify it in order to make better sense out of what kind of plant we can use
And
in
you
the
can
future.
account for the IRA tax credit benefits that you'll have.
Absolutely.
For you also.
Yes, and none of these calculations have any of the subsidiary
Right.
or any of the other numbers plugged in there.
Okay. Okay, I'll buy one.
Any other questions? Thank you so much. I guess that
I was almost
concludes
gonna- I
our
almost put a slide
session.
in there with peak loads and stuff, but I thought that
Can I take a picture of you beside your PowerPoint? Okay.
Sure.
I did, I just wasn't sure what time I was on.
Are you in this session too?
I don't remember, be honest with you. Ben, that's for real.
From Burns McDonald?
Yep. Okay.
Would you like to come in?
Me, or is there anybody else?
No, I think
Okay.
just you.
And my memory stick is not cooperating. So do you guys have it on it? Is that your?
Can't unwrite encrypt it, so it won't let me copy to it.
It's not either one of these, right?
No.
No. But I can plug my laptop into it, or should be able to.
We can try that.
Will we be able to
I
record
don't,
it?
oh, yeah. Do you want it? Is it okay for you to be recorded? Because they're trying to record every session.
Yeah, I think so.
So
No.
we'll have to
Use
let,
this
let me call
laptop.
one of the other guys.
Oh, okay. Or if anybody's got a memory stick that's not right encrypted, I could try that.
Yeah.
Try this. Or try this. We'll figure that out.
It's IT everywhere. I can't escape it.
You mean recorded, not like, you mean just slides? I mean, there's like no video recording.
It's recording the screen.
There was, okay, yeah.
Yes.
No voice or anything.
It captures the voice too.
Oh, really?
Yeah.
Well, I wish I would've known
If I'm walking too far,
that. Oh, no.
not necessarily.
I thought I had a captive audience there. Put a qualifier in there. I can either confirm or deny any statements made. You have to sign a thing that says that you agree to be recorded.
I like
Oh, you go. Oh, boy.
because I'm trying to figure out how to explain, you know, if we can just treat the space load and capture it right here, then we don't have to scale it, we can just keep it steady, you know, temperature, every angle, just always around 24 hours a day. At least 95%. 24 hours a day.
Yeah,
Yeah,
you yeah, because I uploaded it a couple days ago, I think. I don't know if you get it there.
What you're saying, put it in there. I don't want to put it in too many.
Laptop onto a.
No, it says the disk is right protected.
Why don't you email to yourself and then log into email or something?
Okay, we can try that.
Yes. He's trying to email it to himself so that he can open it here.
I tried to, but my USB situation's not working. I don't know if it's,
start talking,
right?
That might take
I gotta do
one
that.
to here. I can
Hotspot in.
The decision.
Yeah. Okay.
Do you have a,
See, if you go to exhibitor, it is capital, visit with a capital V. Irving with a capital I. And then 2024.
I uploaded it to and
Guess it might work too.
VISIT IRVING 2024.
That one, it says guess towards the bottom, you don't need a password. It's pretty slow. It'll still work.
Gotcha.
You might have to do a 20-factor authentication there to get back into your Gmail on a different
Oh,
computer.
really?
I don't know how, what things you got, but I guess you could email it. Old AOL account or something.
Got internet just in case if you want it.
it's gotta be so complicated nowadays.
And technology is the only thing that seems like it's getting harder to use.
Plug this computer into this projector and call it even. Sure, it's not recorded. So, I didn't hear you at the beginning. Are you a professor there?
Yes, sir.
That was
West Texas A&M.
West Texas A&M. So it's Texas A&M, West,
It is Texas A&M
okay.
because they have so much